charge of monitoring earthquakes in Montana. And so what I'd like to do today is talk about earthquakes and some faults, some historical earthquakes. I'd like to keep it very informal. If you have any questions along the way, or I say something you don't understand, please interrupt me and ask me what I'm talking about. I'm happy to explain. And so with that, this is an epicenter map for the last 15 years showing earthquakes in the western United States. Wow. Now normally when you talk about earthquakes, the first people think it's all about California. And it's true that California has a lot of earthquakes, but they're not the only place that has earthquakes. Here in western Montana, we have this thing called the Intermountain seismic belt. It starts down here in southern Utah, runs up along the Wasatch through Salt Lake City, northward along the Idaho-Wyoming border to Yellowstone Park, and then it apparently splits into two branches. One branch runs to the west into Idaho through extreme southwest Montana, and the other branch continues on northwestward up through Helena and up into northwestern Montana. This zone is called the Intermountain Seismic Belt, and it is unusual because most of the time earthquakes occur along the tectonic plate boundaries, like the San Andreas Fault in California and off the coast of Oregon and Washington. And so we have this seismic belt that runs through Montana, and we don't fully understand why it's here. If we zoom in a little bit, this is the map of 42,000 earthquakes that we've located with our seismic monitoring stations since 1982. And again, you can see this band of seismic activity going through western Montana. The orange stars are historic earthquakes with magnitudes larger than 5.5 on the Richter scale. So you can see that the big earthquakes in the past have occurred along this belt where the smaller earthquakes are occurring today. With one notable exception, up here in northeast Montana, there was a magnitude 5.6 earthquake back in 1909. It's quite an anomaly. We also have approximately 75 faults in western Montana that we believe might have possibility of producing a future earthquake. They're shown in red here. It's kind of a chaotic pattern. Although they generally follow the trend of this Intermountain seismic belt, they aren't all lined up. It's not like the San Andreas Fault where one big fault runs through the whole region. So the U.S. Geological Survey has taken both the big historic earthquakes, the modern seismicity, and those faults, and combined all that information to come up with what's called a seismic hazard map. This map shows where seismic shaking of a certain level is most likely. And as you could have predicted, the area down around Yellowstone is kind of the bullseye for western Montana, but the Intermountain seismic belt shows up in these warm colors, which means there is a better probability of having a earthquake big enough to feel in those regions. In Butte, we're right about here, just kind of on the western edge of this, the main part of the seismic belt. And stepping back and looking at it from the perspective of the western U.S., again, California is the main zone of seismic activity, but here is that Intermountain seismic belt coming up into western Montana. Well, let me start off by talking about an earthquake that occurred 10 years ago, last summer. This was the Dillon earthquake. This is a view from Google Earth. Here's the town of Dillon. We're looking up north towards the Highland Mountains, and this red circle represents the epicenter of that earthquake. There is no mapped fault in that area. Rather, this earthquake occurred about 6 miles below the surface. The earthquake was reported by almost 3,800 people to this U.S. Geological Survey website, where you can log in and give your zip code and fill out a little questionnaire how you felt the earthquake, whether it woke you up or whether it knocked things off your shelves or damaged your home. And the colors indicate the strength of shaking, and as you would expect, the strongest shaking was right in the Dillon area, close to the epicenter. And then you can see that the earthquake was felt throughout western Montana, most of Idaho, northwest Wyoming, even into parts of Washington. There was some minor damage from this earthquake. This was in the county planner's office. These shelves were obviously not attached to the wall. It might be hard to see, but this is the chimney on top of Old Main Hall on the campus at UM Western in Dillon, and there's a big chunk of it missing and a huge crack coming down here, and they actually had to disassemble that chimney as an emergency procedure right after the earthquakes. They were worried an aftershock might cause all that mass of bricks to come down through the roof. Some chimneys stood up in spite of themselves. Along Interstate 15, north of Dillon, this is a 1-inch anchor bolt that was sheared off of this pier on this overpass. The overpass was not seriously damaged and remained in service, but that whole cement girder must have slid back and forth on its foundation there. There were some minor cracks in the ground near the epicenter. This is a county road near the epicenter showing a small fracture. And just off the side of the road, running through this field, is a crack here with about 6 inches of displacement. I think this was just the effects of strong shaking. This isn't the actual fault that generated the earthquake extending up to the Earth's surface. So there was fairly strong shaking in the epicentral area, but it was, as you can see, very rural, a few ranches, but 9 miles north of Dillon. This map, the yellow dots, are aftershocks that occurred during the first year following the earthquake. There were over 1,000. The main shock was this black star right here. We put in a new seismic station with the help of the USGS right here, and we're looking down on a map of all that seismic activity. The next shot will be a line looking in cross-section along this east-west line. And here is the ground surface up at the top, and this is 6 miles deep right here, 10 kilometers. The main shock is this red star, and major aftershocks during the first 24 hours are the red dots. Smaller aftershocks later are these black dots, and so we think our interpretation is that the fault covered about this much vertical extent. The right side slipped down relative to the left side during the main shock, and then these minor adjustments, these aftershocks, occurred in the area above the fault plane. So let me jump back in time now to the state's first seriously damaging earthquake. This occurred in 1925, in June 26th of that year. It was centered up in Clarkston Valley, which is a few miles north of Three Forks, up along the headwaters of the Missouri River. The magnitude was estimated to be a 6.6 on the Richter scale, and it caused some serious damage to structures in Three Forks, such as this church, this school in Manhattan, Montana. And this is the best example I can ever show you of why you don't run outside during an earthquake. The walls are standing, the roof is standing. It lost a lot of brick on the top of the walls, which is all now laying down in a pile around the perimeter of the building. And here's the front porch. If you had been running outside of the building during that shaking, it might have been right when the brick was falling 3 stories. Much better to wait inside until the shaking stops and then go outside. In 1925, the railroad was the main route of transportation in and out of western Montana, and this earthquake heavily damaged the railroad tracks by knocking large boulders off the railroad cuts along the Missouri River down onto the tracks. There was a sizable landslide further to the north, and I believe the tracks were down for at least 2 weeks following this earthquake. that would be the equivalent today of shutting down the freeways in western Montana. The next big series of earthquakes occurred in Helena in October of 1935. And I say it was a series because there were over 1,800 earthquakes that were felt over 6 months, and 2 of those were very large earthquakes. The first big earthquake occurred on October 18th of that year, and this map depicts the shaking effects of that earthquake. The epicenter, of course, is right here in Helena, and the little red bullseye is the area where there was considerable damage. There was strong shaking out in the orange area, and it was felt strongly throughout the yellow area. So again, it affected all of western Montana and parts of surrounding states. It did heavy damage to many of the masonry buildings in Helena. This is the county poor farm. There were only a few buildings that collapsed completely, but this was one of them. Most other buildings remained standing for the most part. And this was a house, and the entire front wall fell off, but amazingly the steam radiator is still standing there on the second floor. I understand this was the telegraph office, and obviously there weren't any communications going in or out of Helena via telegraph on this day. This is the Montana Armory. This was the building that was designed to be put into service during a state of an emergency. It was later condemned and had to be torn down. And most amazingly, this was the Helena High School. This was a brand new high school that was opened on August of 1935. This is how it looked on November 1st.
Oh, wow.
And very fortunately, the first big earthquake that started the damage occurred at about just after 9 p.m. when the school was empty. I said there was a series of earthquakes. The biggest one was October 18th, and then 2 weeks later, on October 31st, there was a magnitude 6.0. The first one was about a 6.3. So between those 2 earthquakes, 60% of the buildings in downtown Helena received structural damage, and there were a total of 4 people killed, all as a result of falling building debris. The largest earthquake in our state's history occurred down near Hebgen Lake on August 18th of 1959. This was the first earthquake that was big enough that the fault that slipped caused the shaking, ruptured all the way to the surface of the earth, and this big scar running along the top and along the side of this ridge is the offset that occurred during that earthquake. Here's a closer view of that fault scarp. The ground level up here used to be level with the ground where this geologist is standing.
Wow.
It was up to 21 feet of displacement in places along this fault. This was a magnitude 7.3 earthquake. It produced extremely strong shaking in the West Yellowstone Valley and shook hard enough to literally just shake the pavement to pieces. This is the highway leading south into West Yellowstone. Rockfall was a big problem. Steep hill slopes with rocky outcrops above, huge boulders cascaded down some of the mountainsides. There was some big landslides along the shore of Hebgen Lake that took out the highway. This whole chunk of ground disappeared into the lake. This is an aerial view taken the next morning by the Forest Service. Here's Hebgen Dam right here. And this little white stripe along here is the fault scarp. So the fault came pretty close to the dam. The dam did survive, but it was heavily damaged. This is a view along the crest of the dam showing the old outlet works. And again, the earth-fill material was just shaken into pieces. There was a concrete core wall in this dam, which is a good thing, a cement wall in the middle. You can see it's cracked, and this material down here used to be leveled with the top of that core wall. And so the dam did survive, but it was badly damaged. The movement along that fault actually tilted the whole Hebgen Lake Basin to the northeast, towards the fault. And so as a result, the northeast shore of the lake was flooded. And the southeast shore was left high and dry. Here's the new shoreline running along here, and you can see the old boat docks in front of the cabins out here, high and dry. So that entire lake basin suddenly tipped during the earthquake, and as a result, a huge wave sloshed back and forth in the lake, including, it was large enough that it overtopped the Hebgen Dam at least 3 times. And here you can see the logs that were washed up by some of these waves, and the water that's flooding part of the roadway. There were a number of cabins along this shore that were washed off their foundation and into the lake by those waves. And perhaps the most dramatic effect of this earthquake was the Madison Canyon slide. This entire chunk of the south wall of Madison Canyon collapsed into the valley, into the Madison Valley, and it covered part of the Rock Creek campground down in this area. A total of 26 people died at this site. There were 2 others over at Cliff Lake to the west that were killed by rockfall, and 40 years later, the remains of a climber who had been on Granite Peak were found, and they believe that he was also a victim of rockfalls. So it was a fairly deadly earthquake for being in such a remote area. And the last, call it a historic earthquake, I guess, was the Bora Peak, Idaho earthquake. This occurred over near Chalice, Idaho in October 28th of 1983. It was a magnitude 6.9 earthquake. It also produced a fault scarp that's about 6 feet tall here. It was not as big as the Hebgen Lake earthquake, but in many other respects it was similar. This is looking back at the Lost River Range. That's Bora Peak, the highest peak in Idaho. And the reason it's so tall is because every 5,000 to 8,000 years, an earthquake of this magnitude uplifts the range another 6 feet. So through geologic time, many of the mountain ranges in western Montana and Idaho have formed in exactly this method. This earthquake produced fairly strong shaking in the town of Chalice. This is a historic storefront that collapsed into the street just as 2 children on their way to school were passing, and they were the only 2 casualties of this earthquake. Just want to jump briefly now to look at some of the faults. I showed you this map earlier showing the locations of some of these faults. Well, what do they really look like on the ground? Here's an aerial view of the front of the Madison Range, just south of Ennis. And you might be able to see this little stripe running along the hillside. This is a break in the hill slope, a scarp, that was formed by a prehistoric earthquake. Now, we don't know exactly when it occurred, but if we follow this fault scarp along, we see it crossing the mouth of Wolf Creek here, and a glacier came out of Wolf Creek during the last ice age and left all these deposits along here, and that fault scarp clearly cuts those glacial deposits. So we know that at least one major earthquake has occurred on this range front since the last ice age. I know that sounds like a really long time ago, thousands of years, but in a geologic perspective, that was yesterday. That's fairly young for the geologic record. Here's another fault running along the base of the Tendoy Range, just outside of Lima, Montana. We're looking to the west. This is Interstate 15, and the fault goes right along the base of this mountain range. Here's another view from the air of the Red Rock Fault that we just looked at, crossing the mouth of Big Sheep Creek. And these are big cottonwood trees. They've lost their leaves in the fall, but they're probably 50 to 60 feet high, and this is a huge scarp along there, probably formed by multiple prehistoric earthquakes. And so what can you learn from these fault scarps? The one method is to go out and dig a trench with a backhoe along. This is the scarp along the front of the Big Belt Mountains over east of Canyon Ferry Reservoir, and this is a project by the U.S. Bureau of Reclamation. They dug this big trench, and then exposed in the wall of this trench, you can see various layers that have been offset by the fault. And if you make a careful map of this exposure, such as this is from a trench down in the Centennial Valley, you can see various layers that are offset by faults, some layers that have formed after that fault scarp formed a low spot in the landscape where dust and sand blew in and was deposited. By unraveling the details of these different layers and fractures, we think we see evidence for 6 prehistoric earthquakes in this one exposure. So these faults do move time after time, but it may be separated by periods of thousands of years between major earthquakes. I showed you this seismic hazard map before, and looking at it, you might say, well, this area over here in the Beirut doesn't look like it's too active, and then if you put earthquakes on top of that, you say, well, really, there's not much going on over there. Well, recently, we found out that the Valley County was able to acquire some very high-resolution imagery that effectively removes the vegetation. It's called LIDAR. It's a fairly new but a very powerful tool. And running along here is this break in slope. And in fact, it continues over here, but it looks a little different. It looks higher. This is the end of the deposits from the Bear Creek Glacier. And this red line represents the fault here. And if you look at the amount of offset of the land surface on these 2 sides of the 2 segments of the fault on opposite sides of Bear Creek, this up here is offset almost 80 feet, and down here on this younger geologic surface, it's more like 12.5 feet. So that is proof positive that this fault has moved repeatedly over geologic time. So even though the Beirut Valley isn't one of our hot spots of seismic activity today, there have been big earthquakes there in the geologic past. And this is actually, this information was just discovered in the past couple of years. There's probably other surprises as this data becomes available in other places around the state. I'd like to talk briefly about our seismic monitoring program. The red triangles in this picture are seismic stations operated by the Bureau of Mines and Geology. We have about 35 stations in western Montana that all record data back in my office up at Montana Tech. In addition, we get data from other seismic stations in Washington, Canada, Yellowstone, and Idaho that we also get in real time. So we have a fairly extensive seismic network. And just as an example of what we see, here is the seismic activity for calendar year 2014. Over 2,000 earthquakes. We had a magnitude 4.5 earthquake up near Kalispell last year. Magnitude 4.8 over by Chalice. There's a magnitude 4.8 in Yellowstone. That was actually turned out to be the biggest earthquake in Yellowstone in the past, I think it was 25 years or so. It was a surprisingly long time. And one lonely little earthquake out there in eastern Montana. All of this data goes onto our webpage in near real time. And examples of some of the other things that we see with our seismic network. Of course, we see distant earthquakes. This is a 90-minute recording of the Nepal earthquake from last April, a magnitude 7.8 earthquake that occurred under the Himalayan mountain range. And these are the various seismic phases, the P waves and the S waves, and then way back here coming in for the better part of an hour are the surface waves. So from a big earthquake, the energy expands throughout the earth. It's reflected off various layers and surfaces. And so at distant stations like this one, you get a very complex waveform that is giving you information about the interior structure of the earth. Here is the traces for a whole bunch of stations in our network, and you know this little wiggle that kind of spreads out across here. Those are the P waves of the North Korean nuclear test that occurred in February of 2013. I mentioned that earthquake up in northeast Montana. The epicenter occurred right here, northeast of the town of Brockton. This is a seismic recording from the closest station, which is just off the northeast corner of this map. And everybody immediately assumed that this earthquake being out near the Bakken was an induced earthquake, a triggered earthquake caused by fracking. And so we had to look into it. The red dots here are injection wells. Those are wells where they dispose of minefield fluids down deep into the Earth's crust so they don't contaminate the surface water. And we could not find any direct connection to these injection wells, but the earthquake was centered very close to this long fault here called the Brockton-Freud fault zone. And so we suspect that this earthquake may actually be a natural tectonic earthquake associated with that fault zone and have nothing to do with the activities of man. Here's an earthquake swarm that occurred up in the Swan Valley on August 4th. There's about 60 earthquakes. This is a 24-hour record. Time starts, I'm sorry, it's only 12 hours. Time starts at the upper left and increases left to right along each line. When you get to the end of that line, it moves over, it comes down a line. It's just like lines of text on a page of a book. And the times are labeled over here. Each line is a half an hour long. So the biggest earthquake was only a magnitude 2.7, but there were dozens and dozens of smaller earthquakes over the following hours and actually some of the preceding hours. Earthquake swarms are not uncommon in western Montana.
Mike?
Yes?
You didn't read the magnitude off that chart, did you? I didn't see that.
No,
You just knew that, okay.
Yes, we did not read it off this particular thing, but it was calculated
Thank
from
you.
some of this data. We see other things we don't expect to see. Last summer, we had a day on Limekiln Ridge where we got all these funny little signals, and then we realized that the Butte 100 bicycle race uses this section of the Continental Divide Trail that goes about 50 feet from our seismic station. And so these funny little wiggles in this part of the record are groups of bicycles pounding down the trail towards the finish line.
That's funny.
In this February record from 2003, we saw this funny signal. This turned out to be a small landslide on one of the walls of the Brooklyn Pit. And in central Montana, on one of the old railroad lines near, crossing the Judith River, they were tearing down this old railroad trestle. And once they got the deck off, they would pull these towers over. And that tower that was on the ground weighed over 1,000 tons. And when it hit the ground, it produced seismic waves that recorded on seismic stations over 100 miles away from the site. So it was a pretty good energy source into the ground. And then last February, I came into the office and saw this, I don't know, it was something, but it was not an earthquake. I could tell because the time between the signals was, in some cases, several minutes of time. Seismic waves travel very fast and arrive at adjacent seismic stations within a few seconds of each other. This was minutes. That told me that this had to be a signal traveling through the air, which is much slower. And I still didn't know what it was until somebody pointed me to this website where it turned out to be a Chinese rocket that was re-entering the atmosphere down here over Arizona, and it traveled to the north through the air and was creating a big sonic boom that was traveling down and vibrating around. So it was a sonic boom from a rocket re-entry. Well, building codes in the U.S. are really pretty good compared to many other places in the world, and they do save lives. This is an example off of these two earthquakes. This was the town of Paso Robles, California. The area was struck by a magnitude 6.7 earthquake, and it heavily damaged that building. The roof came down and landed on a row of cars. I believe there were 2 casualties at this site. But this was really the only building that sustained serious damage in a community or a surrounding area that included about 90,000 people. 2 weeks later, and on the other side of the earth in Bam, Iran, was this what they call the Citadel, which is made out of adobe mud bricks on this hill. Apparently, construction started on it 2,000 years ago. There's an entire city of 90,000 people living there. Magnitude 6.7 earthquake, the same size as the one that struck Paso Robles, hit this town, and 30,000 people died. So this kind of construction is very vulnerable to strong seismic shaking. And obviously this type of earthquake doesn't happen there very often because the city has stood for hundreds of years. I got curious after we've seen population shifts in the state of Montana, and I was curious to see how that correlated with seismic activity. The map underneath shows on a county-by-county basis the population change since our last major earthquake, that being 1959. And you can see that the blue counties in eastern Montana have lost population, but some of the counties in western Montana have grown dramatically. And when you look at that with the earthquake information, I guess you have to conclude that people want to live where there are earthquakes. That's where they've been living. Another way of looking at our historic earthquake data is to make a timeline, starting back with the earliest known earthquakes, where we have estimates of their magnitude. This is just a timeline from 1869, which was the state's first recorded earthquake, up to present. And here would be the 1925 earthquake by Three Forks. Here are the Helena earthquakes in 1935, the Hebgen Lake earthquake and its large aftershocks, another earthquake down in Yellowstone Park on the edge of Yellowstone in the late 1970s. But my office started in 1980, and I think you'd have to agree we've done a pretty good job at preventing. Now, when you look at this graph, we don't know if back in the mid part of the previous century was an unusually active period, and maybe, well, there's possible we're missing events from this part because of the low population and reporting, but or perhaps we're in an earthquake drought right now. We just don't have enough historic perspective to know for sure. But in either case, we know that large earthquakes are certainly possible and have occurred both prehistorically and historically in our region. And we'd be foolish not to believe that they will occur in the future as well. Although we cannot predict the time or the place, the safe bet is that they'll occur somewhere along that Intermountain seismic belt. I'll just briefly mention, we were approached by somebody with the Disaster and Emergency Services Division up in Helena. They were doing an earthquake exercise in Butte for training purposes. They wanted a realistic earthquake to base their practice around. And so I used the Continental Fault, which is this red line right here. This is Interstate 15, Butte is right here. The Continental Fault runs along the base of the East Ridge. We don't know how active it is. It's on the map. There's no clear evidence that it's moved in the recent geologic past, but it has not been studied in a great amount of detail. So I took the length of that fault, a reasonable offset, and came up with a magnitude of 6.7 for that, for sort of the worst case scenario on that earthquake. And provided that information to the USGS. They developed something called a shake map that just predicts if you had an earthquake along this fault. Shaking, of course, is stronger close to the fault and weaker as you go away, and that's what this shows. The warmer colors near the fault and getting weaker as you go away. Then FEMA, Federal Emergency and Management Agency, took this shake map and ran it through another piece of software called HAZUS, which is evaluates the hazards from specific geologic events. And it's based on a whole bunch of assumptions, and they use very generic information for our region. But in the brief report that they came up with, they said that depending on time of day, there would be between 8 and 46 casualties for such an earthquake. It would generate over 300,000 tons of debris from broken buildings that would need to be disposed of. And these are their estimates, again, based on very generic databases, but that over 800 million in damages related to buildings, transportation system, over 400 million for the utility system, so a total economic loss of over $1 billion for an earthquake if it were to happen. So it's kind of, we're currently doing this kind of assessment on some of the other faults around western Montana, just to get planners and developers a ballpark figure of kind of what the worst case scenario could be.
What about loss of human life?
Well, that was up here, 8 to 46. Depending on the time of day. If it was right during rush hour when you had a lot of people on the streets in downtown, that would be worse than if everybody was home at, at 2 in the morning when everybody's home in bed. Let's see, we've got a little time. I did some work with a colleague from the U.S. Geological Survey trying to learn something about the oldest seismic events in Montana. It turns out that on November 4th of 1897, there was a big earthquake somewhere in southwest Montana. Of course, there were no seismograph stations at the time to locate an epicenter. My colleague developed a method of looking at how strongly the shaking was felt at different locations and using that information to estimate an epicenter and a magnitude. And on this picture, the circles are sites where we were able to find some kind of information about the strength of shaking. In a paper, it said something like, books fell off the shelves, or people were awakened and ran outside because of were frightened and ran outside. And so these various numbers here from intensity 6 down to intensity 3, 3 being weaker shaking. I spent a lot of time combing through old newspapers trying to find information that would allow us to get as many points as possible. As it turned out, we have not an overwhelming number. It looked like the epicenter was probably somewhere down east of Dillon and probably about a magnitude 5.8, but that's a lot of uncertainty. But in the course of combing through these papers looking for useful information, I found some not very useful but entertaining information, such as this from the Anaconda Standard, which said that Butte seems to be improving in the matter of earthquakes. At least that is the general opinion. That the one which came along here at 2:30 o'clock yesterday morning was the most enjoyable Butte had ever experienced. There was some style about it. The old earthquakes did well enough in the days when Butte was a camp of shacks, but now that the city has advanced to the stage of paved streets and 6-story buildings and wine suppers, it takes a good-sized earthquake to make an impression. From the Helena, the judge says that some hackmen across Main Street in front of the Helena cab office evidently felt the shock, for one of them ripped out an oath that would have done justice to a sea captain. The shock at the courthouse was especially felt, and Judge Clancy, who occupies a room in the upper story, tumbled out of his perch and rushed to the corridor in a suit that was anything but dressed. There he met Janitor Rooney, who was also a little short of clothing, and the two exchanged congratulations that they were alive. The judge says his first idea was that some of the sticks that prop up the mines under the courthouse had given way and there was a cave in. As the quake was a purely Montana affair. There is no doubt that it originated in Helena, which is the center of earthquakes as well as everything else. From Helena it traveled south. And this is my favorite. The moral effect of the shock will not, it is thought, be lasting. It is known that some Butte people swore off after that shock, but it is credibly reported they were drinking again yesterday. And I mentioned earlier this LiDAR, this ground imaging technique, and I just have 2 slides here just to show what I was talking about. This is an image of Google Earth looking down on a piece of the backcountry in northeast Yellowstone, Wyoming. And it's hard to see, but there you might see a little faint line there and something over here. The geologist would say, oh yeah, there's probably something going on there. Well, at the same scale, here is this LiDAR image overlaid, and all these straight lines, these little breaks in the surface are all faults that were formed by movements of the ground. You can also see tiny little landslides that have occurred up here. The detail and resolution of these images are just absolutely mind-boggling if you've ever spent any time looking at aerial photos trying to figure out the geology of a site. This is the mother lode of information. Another example from the east side of the Teton Mountains. This is in Teton National Park. The base of the mountain range is somewhere in here, but the LiDAR data, with it you can see the Teton Fault coming right across this valley here. This valley was fed by a glacier. Here are the 2 edge moraines, and here's the end moraine from this glacier. You can see little recessional moraines, and the fault clearly offsets those glacial deposits, again indicating a major earthquake in relatively recent geologic past. So I'll stop there, and I'd be happy to entertain any questions if I can. Yes?
I remember the 1959 earthquake. What made it different for me, I lived in California for a long time and was in a